Hi, my name is Hemant. I'm from University of Waterloo. I'll be presenting our work about cloud-native architecture for replicated data services. This work is done in collaboration with Jeffrey Pound from SAP Labs Waterloo. Here is the outline of my talk. I'll start with describing the problem and motivation behind it. Then I'll give an overview of our proposed solution along with the details about our proof of concept implementation in two very different open source systems, Kafka and Cassandra. With our proof of concepts, we demonstrate that our proposed solution is general enough, and then I conclude with some evaluation of our solution. The main motivation of the problem comes from deploying applications on cloud. Cloud has become a de facto standard for deploying applications due to multiple reasons, such as ease of use, pay-as-you-go model, and flexibility to choose from different kinds of resources. Therefore, many application developers find it easy to host their application on cloud. However, many of these applications were designed with on-premise infrastructure in mind and find it challenging to leverage the cloud storage. Main reason being that many applications rely on application level replication to provide fault tolerance and high availability. In an on-premise deployment, it is common for resources to fail, and hence it has become a responsibility of the application developer to design architectures such that failures can be handled. And an age-old solution to handle failures is replication. Cloud services, on the other hand, already provide fault tolerance and high availability using replication. Therefore, when these applications are deployed on cloud, they end up with redundant application-level replication, introducing additional storage cost. We illustrate the problem more clearly with a sequence of diagrams. Here we present a replicated application on-premise. The outer rectangle represents the replicated application to which a client can connect. The application consists of multiple nodes or machines, each consisting of its own local storage. And a subset of these nodes constitute a replica set within which data is replicated. If the replication factor is 3, then the replica set is supposed to contain 3 nodes. Here we show the application's architecture when deployed on cloud. The storage and compute is decoupled, and local storage is simply replaced via a cloud storage service. The application still maintains its replica set, and the cloud storage also internally uses replication to provide fault tolerance. Hence, we end up with redundant application-level replication and increased storage cost with no additional benefits. In this work, we ask the following research questions. How can we easily allow replicated application designed for on-premise setting to efficiently leverage the cloud storage? We now move towards describing a solution. A naive solution to get rid of the redundant replication problem would be to not allow replication at all. Or in other words, allow for only single replica at the application level. This solves the problem of redundant replication, but does not provide high availability because of the single point of failure. Another straightforward solution would be to share the single copy of primary data stored on cloud with multiple nodes in the replica set. As shown in the figure on the slide, multiple nodes of the replica set can read and write from the same storage instance, which hosts the primary copy of the data. This approach fixes the problem of high availability, which was the drawback of the naive solution described in the previous slide. But this approach has its own drawbacks. First, the cloud storage I/O becomes part of the critical path of read and write operations and hence increases the latency. Second, the shared nothing systems like Cassandra, the storage needs to handle concurrent read and writes and thus become a point of contention. To solve this problem more effectively, we propose a main delta-based cloud native architecture. The main delta architecture is well known for handling mixed workloads. And in this work, we show that it can be used to leverage the cloud storage efficiently. That is, ensuring no redundant replicas while maintaining the fault tolerance and availability guarantees of the application. We also show that incorporating main delta architecture in existing on-premise applications is easy by controlling how buffers are managed and flushed to storage. And it is compatible with the whole spectrum of replication strategies. Before describing a solution, we give a quick overview of the main delta architecture. This architecture was originally designed to efficiently handle mixed read and update workloads. As the name suggests, the architecture has two parts, a main part and a delta part. The main part is read-only and hence read-optimized. Delta part accepts inserts and updates and a small amount of reads, and hence it is write-optimized. At regular intervals when delta is full, it is merged with the existing main and a new main is generated. Now coming to our solution, we incorporate the main delta architecture in replicated applications by having deltas stored locally at each replica node. The deltas could be stored either in memory or on a local disk, and the main is stored at the cloud storage. There is a single application level replica of the main, which is shared across all the replica nodes, but the deltas are replicated at the application level. And typically, deltas are order of magnitude smaller than the main. And now the challenge that remains is how to merge the deltas with the shared main. We need to merge deltas ensuring that no updates from any of the deltas are lost, and the application experiences the same guarantees of fault tolerance as it did in the on-premise deployment. The delta merge strategy happens to be dependent on the replication strategy used by the application. For example, if there is a single primary replica, then only primary nodes deltas needs to be merged. However, in a complex case of peer-to-peer replication, deltas from multiple nodes needs to be merged. We expand more on this in a few slides. We first start with a quick broad classification of prevalent replication strategies. These strategies could be put into three categories. First category has a single primary replica, and reads and writes are handled by the primary replica, and the remaining replicas are used only if the primary node fails. The orange arrows from the request handler to the replica set represents writes, and the blue ones represent reads. An example system in this category is Kafka. The second category is where writes are still handled by the single primary replica, but reads can be served by any node in the replica set. And MongoDB is an example here. And the third category is where reads and writes can be served by more than one node, either all or subset of those nodes. Systems that use quorums of nodes to read and write are also part of this category. An example here is Cassandra. I now move on to explain how main delta can be adopted for different replication strategies and how the delta merge is done. We show this for systems with single primary replica and quorum-based system, which are at the two ends of the spectrum of replication strategies. First, I describe it for Kafka, which is a single primary replica system. Here we manage the in-memory buffers and use them as deltas, and use the remainder of the on-disk data as main. Note that this on-disk data is hosted at a cloud storage, which internally replicates the data and provides fault tolerance and high availability. Since this system has a single primary replica, the delta merge strategy is simple. We just need to merge the deltas from the primary node to the main. Reads will be served by both primary nodes delta and the main. And in the case of primary node failure, Kafka automatically elects the new primary node, and we hand over the delta merge responsibility to the new primary. Next, I describe delta merge for Cassandra, which is a quorum-based system, very different from Kafka. In Cassandra, the reads and writes are served by a quorum of nodes. For example, if replica set contains 3 nodes and write quorum is 2, then each write request is considered committed if at least 2 nodes out of 3 have locally committed the write. Read quorum can be described similarly. To incorporate main and delta in Cassandra, we treat Cassandra's mem tables as deltas and SS tables as main. Then since each of the node in the replica set can contain different set of updates in its delta, we need to merge deltas from all the nodes. We do it in the following way. Each node flushes its delta to the shared cloud storage. Then we piggyback on Cassandra's compaction job to merge these deltas into single delta and then merge it into the main. In the figure, we show 3 deltas from 3 different nodes, and no single delta has a complete set of updates. We then show that these deltas are flushed to cloud storage and merged to main via a compaction job. With this approach, the only overhead is that we see redundant replicas of the deltas for a short period of time. That is, until the compaction job picks up these deltas and merges them to the main. Since we do not change the flush semantics of Cassandra, the durability guarantee stays the same. We only modify the compaction job so that it can merge deltas as well. We now show some experimental evaluation of our solution implemented in Kafka and Cassandra. In our evaluation, we want to show that our approach can result into storage cost savings without impacting the performance. We performed our evaluation on Amazon Web Services using 2 different types of storage, EBS and EFS. And to generate workloads, we used performance tools that are already part of Kafka and Cassandra system. For Kafka, we measured the write throughput since it is a message broker service. MD Kafka, as mentioned on the slide, is the main delta-based implementation of Kafka, and Kafka is the original Kafka. First of all, with the application level replication factor of 3, we saw 3x storage savings by design. And that is because only the primary replicas deltas needs to be merged to the main. We tested the write throughput on block storage, that is EBS, and observed that throughput of MD Kafka and Kafka are almost same. Then we tested them on NFS-like storage, that is EFS, and observed that MD Kafka performed almost 2x better because of main delta architecture batches the storage IOs. We now show the evaluation of Cassandra. In this case, we observed almost 2.8x storage cost savings with replication factor of 3. And that is primarily because deltas still have redundant replicas for a short duration. We compare the throughput of main delta-based Cassandra with original Cassandra implemented on cloud storage, and we saw similar throughput for all 3 types of workloads. Those are read-only, write-only, and read-write mixed workloads. I now conclude my talk by pointing out the key takeaways from this work. We showed that existing on-premise application with replication ends up with redundant replicas when deployed on cloud. We propose a main delta-based architecture to solve this problem, allowing for a storage cost savings while leaving the performance and failure guarantees unchanged. We showed that our approach is general enough to be adopted for the complete spectrum of replication strategies. With that, I would like to thank the audience for their time and thank my co-author Jeff and other collaborators at SAP for their time and effort.